Today we're going to continue looking at integration by substitution, which is our anti-chain rule. Remember what we're looking for. We're looking for something that we can call the inside function. And to make that substitution happen, we need to have something to stand in as the derivative of the inside. So we have to look at a function where it looks like we got this derivative from the chain rule so that we can undo that with substitution. So let's take a look at our example for today. I've got sine cubed of x times cosine of x dx. What we're looking for is one function to be seen as being inside the other function. We need to see a composition of functions. So in this case, I've got this sine cubed x times cosine x dx. So it looks like our inside function should be sine cubed, or sorry, just sine. When we write sine cubed, remember that this is our shorthand for writing the sine of x, or I should say the cube of the sine of x. So even though we write sine cubed x, we read it as the cube of the sine of x. And so we want to be able to see that as a sine x being inside of a cube. So here's our inside function. If we're going to call sine of x the inside function, we have to identify the outside function. And so y is equal to w to the third power. So the function that we're actually going to integrate is a third power. Now we have to make sure we have the parts to make this substitution work. The derivative of sine is cosine. And that's what we have here, that this cosine of x and the dx will all become dw. So our integral in x after substitution becomes the integral w to the third power and that cosine x dx is all dw. So we've traded our super complex integral in x for this simple integral in w. The integral of w to the third is 1/4 w to the fourth plus some constant. And w is sine of x, so we'll have 1/4 times the sine, the fourth power of the sine of x. Plus c, of course, because we don't want to lose a billion points. The important part of the process, aside from all this stuff where we need to be able to read powers of trig functions and whatever algebra in trig is associated with it, once we identify the substitution that we want to make, we have to make sure that we have some factor to be the dw. We need something to be the dw. To make this substitution, w equals sine x, I need to have a factor of cosine x dx to be the dw. I can only be different from that cosine x dx by a constant factor. So to make the substitution, w equals sine x, we need to make sure that we have a dw. So it's not just that we're how we pick we're going to make this, what substitution we're going to make, but how we know we can make that substitution. What else do we need to make that substitution happen? So for example, if I drop the cosine out of this most recent integral and just had sine cubed x dx, in this case, we can't make the substitution w equals sine x because we don't have a factor of cosine x to be the dw. So in this case, we can't make the substitution w equals sine x since we don't have a factor of cosine x to be dw. We can't make the substitution w equals sine x because that requires a factor of cosine x to be the dw. So if w is equal to sine x, we will need a dw equal to cosine x dx. And that is not available. It doesn't mean that we're not going to do substitution on this integral. It just means we're not going to do this substitution where w is equal to sine of x. Any questions? So it's not that we're not going to use substitution. We're just not going to make this substitution. The strange things that we have to do with integration by substitution is we might be making substitutions that we don't actually see yet. So here we have sine cubed of x dx. The substitution that we're going to make is actually cosine of x. Mostly because we can turn an even power of sines into even power of cosines, and that will save us one factor of sine to be the dw for a cosine substitution. So let's see what the actual substitution looks like in this problem, because it's a little bit sideways. So we know that sine x is not the substitution. But we also notice that we have an odd power of sines. So I can write this as sine squared x times sine x dx. Because I have an odd power of sines, I can save one factor of sine of x, and that's going to be my dx. But not for sine, it's going to be for cosine. Since I have an odd power of sine, I get a sine squared, and that we can turn into a cosine. So this is equal to the integral of 1 minus cosine squared x times sine x dx. So because I had an odd power of sine, I could save one to be the dw for a cosine substitution. If I make w equal cosine x, I'm plugging it into the function 1 minus w squared. And the reason that I want to make a substitute into 1 minus w squared is that the derivative of cosine is negative sine. And that's that factor of sine that we saved to be the dw. I have to change the sign here. dw minus dw is sine x dx. So this sine x dx, that's going to be replaced with minus dw. So we had to come at this one sideways. We had to look at what was there, sine cubed of x dx, and think about what we need to make a substitution go. I need to have something to be the dw. Since everything's in terms of sine, I can save one factor of sine to be the dw, replace the other two factors of sine with 1 minus cosine squared. So my integral becomes uh, 1 minus cosine squared x is going to be 1 minus w squared. And sine x dx all gets replaced with minus dw. We have traded our x integral for a w integral. Now all we have to do is integrate. Note that there's a negative out in front of a subtraction, so I'm just going to reverse the order and call this w squared minus 1. So we integrate in terms of w, so we get 1/3 w cubed minus w plus c. And then we remember that w is cosine x, so I get 1/3 cosine cubed x minus cosine x plus c. So this was still a substitution problem. It's just not the obvious substitution problem. The substitution w equals sine x doesn't work because we don't have a factor of cosine x to be the dw. The other thing that we have to remember from trig is that it's easy to turn an even power of sines into an even power of cosines. So we don't want to think of learning integration by substitution by some recipe. We need to know how the method works so that we can adapt it to a variety of situations, especially if you have to come at a problem sideways like we did in this problem. Notice that if I change this sine cubed x to a sine to the fourth, all of a sudden it stops working. What we did here won't work anymore. So if I have, for example, the integral of sine to the fourth x to x, if we save one factor of sine to be the dw, we're left with an odd power of sine, and that is not going to convert to cosine cleanly. It's easy to take an even power of sines to an even power of cosine, but an odd power of sine does not translate to cosine very well. So odd powers of sine and cosine don't translate well. we'd end up with some radicals showing up. So sine squared is 1 minus cosine squared. Even powers of sine and cosine are easy to exchange. Even powers of sine and cosine are easy to switch. Odd powers of sine and cosine don't translate well. I would have to write this sine cubed x as sine squared x all to the 3/2 power. And then, so this would become 1 minus cosine squared x to the 3/2 power, which is fine. But now we have to integrate 1 minus w squared to the 3/2 power, and we don't have machinery for that. So the substituted integral would be 1 minus w squared to the 3/2 power and we don't have an integral for that. It'd also be a -1. Doesn't mean we can't substitute. It just means that this substitution leads to a place that we can't cope with yet. However, if I have this sine to the 4th x, and there was a factor of cosine x involved, now it's just 1 degree higher than my original example. W can be sine x. dw is cosine x dx. And the function we're integrating is a 4th power. So the integral of something to the 4th power is 1/5 of that thing to the 5th power, plus some constant of integration. And w in this case is sine x. Any questions?
Yes, for Professor Leach, could you please scroll up to the top? How do you get 1 on the second line? How do you get 1 minus cosine square x? I know you get it from the sine.
From the sine squared.
Right. How do you get
Sine squared is equal to 1 minus cosine squared. That's a trig identity.
Okay, and then
Cosine squared x plus sine squared x is equal to 1. So we can turn that around and solve for sine squared. To find sine squared is 1 minus cosine squared.
Okay, thanks. And then on the second example, we have the similar. When you get the substitution, that we have like on the second example on the right to the third, And once you get this substitution, like to 1 minus cosine square x, and then to the power 3 over 2, it cannot be because of that 3 over 2, am I right?
Yeah, we can replace the sine squared with 1 minus cosine squared, but we still have this exponent of 3/2 that's
Yeah.
sitting on top of everything. And we don't know how to integrate that without an extra factor of w.
Oh, okay, thanks, Professor Liz. Thanks for the added identity. Thank
Yeah.
you.
Professor, one more question. On the example above that, where it says 1 over 3 w to the third power minus w plus c, where does the minus w come from?
We have to integrate both of these terms. The integral of 1 is w.
Oh, okay. Thank you.
Any other questions? So the exercise here is not about integrating products of powers of sines and cosines. That's not the goal. The goal is to understand the process of substitution and remember what's required to make a substitution. So the substitution in this case, w equals sine x, what we need to make that work is a factor of cosine x that can be our dw. And we have that. In the previous example, I can't make the substitution sine x because I don't have a factor of cosine x to stand in as dw. So that substitution, w equals sine x, won't work. That was the same thing that happened in the first example. W equals sine x would not work because we don't have a factor of cosine x to be the dw. However, this problem we can employ some trig on and say one of these factors of sine is going to be the dw for my cosine substitution. The reason that works is that once we save a power of sine to be the dw, we're left with an even power of sine that we can convert to cosine. This only seems like a lot to remember because it's a lot to remember, and you have to remember all of it all the time in perfect detail. Now, keep in mind also that our goal is to not have to write what our substitution is going to be and just be able to get to the result. So the goal, it should look like this. Let's suppose that I have the integral of x to the fourth times the sine of x to the fifth dx. We want to avoid having to write down what our substitution is going to be. We just want to see that this x to the fourth can be the dw, where w is x to the fifth, but we'll be missing a factor of 5. And the integral of sine is negative cosine. So I'll have negative from that 1/5 cosine of x to the fifth plus c. So when I say show your calculations, this would be perfectly sufficient. The goal is to not have you write down every detail. You start writing down every detail to help you get to the point you don't have to write that down anymore. So you start off by saying, I'm marking x to the fifth as my inside function, so that's w. If w is going to be x to the fifth, I'm plugging it into the sine function, so y is sine of w. That's the function I'm actually going to be integrating. And then I say if w is going to be x to the fifth, then dw is going to be 5x to the fourth dx. That's what I need to make this substitution work. I don't have 5x to the fourth dx. I've just got x to the fourth dx. So I just divide by 5 and say 1/5 dw is x to the fourth dx. So that this dividing by 5 is where the 1/5 comes from. The negative comes from the fact that we're integrating the function sine and the integral of sine is negative cosine, because the derivative of cosine is negative sine. The goal is to not write the details. The goal is to skip over all that. You pick up a baseline of things. You pick up that you have to remember that 7 times 8 is 56. And then you need to understand multiplication to the point where you can say 72 or 70 times 8 is 560, because that's what happens in multiplication. And then you need to say that so 72 times 8 is just going to be 560 plus 2 more 8s. So 516. You want to understand how all these things go together so your times table just doesn't become infinite, where you have to memorize every product. You memorize that first chunk of everything from 1 to 10, and then you learn how to expand that beyond. You learn some basic maneuvers. The integral of w to the 4th is 1/5 w to the 5th. And then you expand that with this substitution business. You learn that the integral of sine is negative cosine, and then you expand it to have something else inside the sine. Any questions? You don't want to have to write down the 72 times the 8 in a vertical format and go 8 times 2 is 16. And then you like carry the 1 and put the 6 down here. That was just for training purposes. And that's your training wheels. You want to learn the multiplication well enough that you don't have to do that every single time. Oops. We have run into Calc 3. It's page 3 already. Page 3. So for example, if I had the integral of sine of x to the 5th to x, that substitution that we made in the previous example is not going to fly here. If we make the substitution, w is x to the 5th, and imagine that x to the 5th is in y equals sine of w. When we get to the next parts, when we look for dw, dw is 5x to the 4th dx. I don't have a factor of x to the 4th to be the dw, so this substitution, w equals x to the 5th, will not work. Since we don't have a factor of x to the 4th to be the dw, the substitution w equals x to the 5th does not work. We shouldn't be sad about that. I don't know why I'm expressing that as sadness. It's fine, because we know something. We're not just plunging on ahead, assuming that things are going to work out. We know something is not going to work, so we've learned something. That's +1. We may not have learned how to integrate this function, but it's still progress because we know how not to integrate this function. We know the substitution that's not going to work. Let's look at another weird use of substitution. So this is a bit of a strange one. We see one function clearly inside another function. That x plus 1 is sitting inside a square root. But there's that other x out there. So if we just go with our instincts on this and say, well, it looks like x plus 1 is in fact sitting inside. So w is equal to x plus 1. That's sitting inside the square root function. Y is the square root of w. That's the function that we're actually going to be integrating. Then we got to think about what we need to make this substitution work. dw is just 1 times dx, and I've got that. The question is, what do I do with this extra x? Because the rule for substitution is all x must be w. All the x's have to be substituted. So this square root is no problem. That's going to be the function that I thought I was going to be integrating. This whole x plus 1 can just be replaced with w. The dx is just directly replaced with a dw, but that still leaves us this x out front to be dealt with. Fortunately for our heroes, we made a linear substitution. W is equal to x plus 1. If we solve that for x, we find out that x is equal to w minus 1. Now this looks similar to what we had before. There's still a square root and there's still this linear factor. The important thing is the linear factor with 2 terms is no longer sitting under the radical. The radical part is just a w to the 1/2 power. So I can read this as w minus 1 times w to the 1/2 power, and then just use the distributive property because it's multiplication distributes over addition. So I can write my w integral. We're not integrating yet. We're just rewriting our integral as w to the 3/2 minus w to the 1/2. If we can write powers of w, maybe we should. Once we have terms that are powers of w, we can just integrate by adding 1 to the exponents and dividing by the new exponents. Then we have to recognize that w is not the integral we were looking for. We're looking for an x. You just replace the w with an x plus 1. The issue here was we had two terms where it was very inconvenient to have two terms. We couldn't use the distributive property to get somewhere better. We could have distributed our original x into the radical and written this as the square root of x cubed plus x squared, but that doesn't help because we can't integrate that function, that square root function, the square root of x cubed plus x squared. That doesn't help. The positive part of this trick is that it leans into your natural instinct to look for something that's an inside function. X plus 1 is definitely inside that square root, so it's a natural choice for a substitution. So in that regard, this is better than that weird sine one, where there's no cosine there, but that's the substitution that we're going to make, because one of those factors of sine is going to be the dw for my w equals cosine. Any questions? All right. There are a few of the more interesting applications of substitution, the ones that are a little less obvious. One that had to use a little bit of trig, one of them that had to use a little bit of algebra. But they were all following the same principle. When we're going to try to make a substitution, we have to make sure that all x can be substituted. That includes the dx. We've got to save something to be the dw. Once you decide to try a substitution, you have to figure out what else you need to make the substitution work. We're trying to get to a point where you know when a substitution is going to work or not. Just like with equations, when you're solving equations, you should never have to look up if your answer is correct or not, because it's an equation. You can check your answer. And the same thing is going on here. You don't have to worry about whether your substitution is correct or not. You can see if your substitution is going to work. The trick is not knowing the technique. The trick is knowing when the technique will work. And you'll have also knowing when the technique is leading you wrong, when the technique is not going to work. We're trying to get away from the mindset where we just kind of blindly follow the recipe. We have to be able to see when the recipe isn't working and then know what adjustments to make. If we're trying to make cookies, we have to be able to look at the batter and say, there's something wrong with this batter. And then decide it needs more water, it needs more egg, it needs more whatever to counter whatever problem has arisen. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.